and the first one is given by Ferran Macià. Ferran has 2 degrees in mathematics and telecommunication engineering obtained at the Polytechnic University of Catalonia, and a PhD in physics at the University of Barcelona. He was a postdoc and a Marie Curie Fellow at New York University, and he now works at the University of Barcelona. His research is focused on spintronics in mesoscopic systems, magnetic quantum tunneling and coherence in nanostructures, and perturbations and dynamical systems. Thank you very much for your availability, Ferran, and please give us your talk.
There I go. Okay, so thank you, Jose Miguel, and let me also thank the organizers for letting me lecture in this fantastic course. So today, well, I should share a screen. My lecture is about SpinWaves Spintronics. So let's see if it comes. Okay, so I guess you see it. Let me know otherwise, Jose Miguel.
Yes, we can see it.
Okay, so now it moves. So here's the outline. So this is a lecture on SpinWaves based on, let's say, spintronic applications. So my goal is to basically show you what are SpinWaves, what are the main relevant interactions that result in a particular frequency. We have seen something in the previous talk with Tim, what are the resonant frequencies, and also what is the spatial distribution. So we have modes, right? So we have waves, and that depends on the interactions. I'll briefly discuss or just say something about magnetic resonances and the relationship between spin waves. But probably we'll hear more about this with Adriana in the next talk. And in the final part, well, not the final part, let's say the second half, I want to show you some state of the art on how to create spin waves, how to detect spin waves, and also how to, let's say, modify propagation, what is called magnetic crystals. Okay, so it's this part. And finally, if time permits, so we'll see also some state of the art on what are they used for in spintronics. So the main uses or the main, let's say, goals on using spin waves. Okay, so first definition. We can see several definitions, but spin waves are basically propagating disturbances in the ordering of a magnetic material. This is a fundamental physical definition. We can also see it as a mathematical definition. So these are solutions, dynamical solutions of the Hamiltonian or the energy system. You have a magnetic energy and you have solutions. You have the static solutions that corresponds to having the magnetization in one direction, but you can also have dynamical solutions, and these are spin waves. Well, here I wrote that from the equivalent quasi-particle point of view, spin waves are magnons, and these are actually bosonic modes of the spin lattice. Here in this graph, what I show is the first, let's say, the first evidence. This is an indirect evidence of the existence of spin waves, and that was about 100 years ago. And this measurement is showing the magnetic moment, the magnetization saturation of a magnetic material as a function of temperature. And what was seen is that there's a law that shows that when you lower temperature, what happens is that the magnetic moment increases. So I prefer to say that when you increase temperature, you lower magnetization. And this is because you thermally excite magnetization dynamics spin waves, and these spin waves are just lowering the magnetic moment. This is called the Bloch law, and it goes, I mean, the magnetization, it goes as the temperature to the 3/2. Okay, so in principle, the magnonics term should only refer to to quantum phenomena, right? This is how I define it. But you will see that absolutely everyone uses it in general in a classical way. So magnetization dynamics is kind of a synonym of magnetics. Okay, so we're going to use it in a classical way in general. Okay, so I told you that the Bloch law is the first indirect confirmation of the existence of spin waves in nature, but later on, FMR, and Tim introduced you, the FMR ferromagnetic resonance was a more direct evidence of the existence of a magnetization dynamic. So if you excite the system with a particular frequency, this frequency is absorbed, and that you can assume that the system is processing at that particular frequency. Later on, with a different technique, which I'll discuss later on the talk, it was confirmed that you can have spin waves with some, let's say, lateral or variation in space, which means non-zero wave vector. So in principle, we can think of spin waves to be similar in some short as other waves we know, like such as sound waves or light waves. So in spin waves, we'll be able to excite spin waves. They can propagate, they reflect, they refract, they interfere, and actually they also have interesting effects such as tunneling, Doppler effects, or they can form solitons, right? Okay, so the field of magnetics in general, right, not only in the quantum phenomena, basically tries to study all dimensions of observation: interference, diffraction, reflection, propagation, excitation, measurements, different materials, right? And I wrote that the main goal, as in the case of Spintronics, could be to carry and process information at the nanoscale. So this is, to me, one of the main purposes. Okay, so this is a lecture, and my goal is to give you some basic concepts. So I want to tell you and make sure that you understand what are the resonant frequencies and what are the dissipation relations for spin waves in general. I won't enter into, let's say, deep detail, but let me just recall you that we know, let me see if I can find some other color. Okay, we know that the torque made by a magnetic field on a magnetic moment is just a vector that it's an axial vector perpendicular to both m and h, right? And by the Newton's law, we know that the angular momentum, the variation of angular momentum is the torque, and now connecting both, right? We know that the magnetic moment is connected to the angular momentum by gamma. They are aligned. And we can get an equation for the magnetization dynamics. We've seen this with the damping term. We'll come to that. But this is just the precession. And if you didn't see, this is just the equation of an oscillator, right? And the frequency is exactly gamma h. Okay? So this is important. If you know what's the value of gamma, so you will know exactly what is the value of the precession. So this is the first thing we have to have in mind for magnetic dynamics. Okay, so now what I do is I add the dissipation term, and this dissipation term is going to tell us for how long the excitations last and how long do they propagate. So this is important, but this is not setting, and this alpha is not changing the frequency or the dispersion relation or the wavelengths of the excitations. So what do we do? Okay, so how do we learn how to get the frequency in more complicated systems? So we have an effective field. So the effective field, Tim already mentioned it to you. So is the derivative with respect to the magnetization of the magnetic energy, right? So if you know the magnetic energy, you can know what is the effective field. So maybe one can think that the resonance frequency might be gamma H effective. But this is only correct if H effective depends or does not depend on the magnetization, right? So if the effective field has an applied field plus something else, it's fine. But when this has something like the exchange, that you have something like this, what happens here is that depends on the magnetization. So the frequency is not going to be directly the effective field, but it's going to depend on the variation of M. So it's going to introduce a K vector, a wavelength. Okay. Another way to do that is just put this. So say a solution of M, which is you have M, let's say M0, and then add a small perturbation MS or M that depends on the position and time of this type. So if we do that, we can get what is the frequency. And this is a good exercise. So here, I'll do that. I'll do that in the next slide. But one of the questions I put was, what are the relevant interactions? So there could be many, many different interactions. Actually, we've seen in the first talk today with Andre that the DMI interaction can lead to complicated and fascinating, let's say, objects. Okay, but I'm just going to focus on two particular ones, which is the exchange. The exchange is a very local interaction between magnetic moments, right? So we have overlap of electronic wave functions. So basically, one magnetic moment interacts with the next one, so with the neighbors. And dipolar energy or dipolar interaction is the magnetic field created by one dipole, and this has a long range interaction. So this M goes very far. Probably you will hear that there are exchange spin waves and there are dipolar spin waves. Sometimes the dipolar are called magnetostatic waves. In most of the times in spintronic devices, we have a bit of both. So we have both contributions, okay? So I'm not gonna stay with the naming here. Okay, this is one of the, so this is a lecture. I wanted to put you a couple of exercises. So let's consider a spin chain. So you just have a spins one next to the other. And I want to see what is the resonance frequency, and if that depends, if it's uniform or if it depends on the K vector. Okay, so here we have the energy. So we have a Hamiltonian, right? That is minus 2J. So if I just do a spin chain, what I have is that I have SP dot, this is a vector, SP minus 1 plus SP plus 1. So I'm just considering the two neighbors. Okay. Another thing we know is, as we said before, is that the magnetic moment associated to a spin is G mu B SP, or G is 2 for a spin, electronic spin, right? So now we can write that down and say that, okay, so this is mu, the magnetic moment, and we have a constant, which is 2J over G mu B times dot sorry, SP minus 1 plus SP plus 1. Okay, so look at this. This is a magnetic moment times dot, sorry, something that I'm going to call it an effective field. Okay, so this is kind of a Zeeman energy. This is, we have a Hamiltonian, which is mu p minus magnetic moment dot another vector, which is a magnetic field. So we know, and I just mentioned it in the previous slide, that the variation of angular momentum, in this case, the angular momentum is the SP, so dt SP is equal to the torque, and the torque is the magnetic moment cross the field, which is BP. Okay, so I'm not going to do the whole exercise. Okay, it's just that I'm putting the basis. Sorry, there's an H bar here probably, and so one can just substitute what I have here and end up with something like, okay, the variation in time of the spin is equal to 2J over H bar SP. And look, this is a cross now, SP minus 1 plus SP plus 1. Okay, we have an equation. We have a motion, equation for the motion of speed, the dynamics. So now we can try to just solve these. And the only thing for this exercise you have to take into account is that, let's say, the components, so this is a vector, the components x and y are small, and the z component is basically fixed, and it's more or less constant, and the value of s. So if we take this into account, right, and we say a solution of this type for x and for the same for y, and we just change the amplitude, and if you guys do that, so it's just like a cross. So this is a very simple exercise, but to me it's very important, because the thing we're going to find is that H bar omega is let's see if I'm not wrong, should be 4JS, right? 4JS 1 minus cosine of PA, KA. Okay, and you know that the cosine for small values of this wave vector or x, what we have is this is 1 minus x squared. Well, x is Ka. So these can be approximated by 2JS. And this is important, because probably you've heard that spin wave dispersion relation goes as k squared. And this is different from phonons and from electromagnetic waves, right? So normally we have a linear dispersion relation, and we have seen right now that if we have spin waves with exchange interaction, what we get is that frequency goes with k squared. And this is one of the main differences. Okay, another exercise. I won't do anything here. So let's see what happens if we add something else into the Hamiltonian, and just consider an anisotropy. So this is a magnetic anisotropy. You can do the same chain, and you just take these that depends on the spin. There's no neighbors. So if you do that with the same procedure, you will get that the frequency is the same term we've got, plus a constant that depends on the strength D of the single ion anisotropy. And that means that what happens here is that this interaction, this magnetic energy is just lifting the frequency. So if I plot it here, we have a square, this is K and this is frequency. So we have something like this. And if you change the energy, this goes up, so we can lift it up. This is also another important feature of SpinWaves. So this is just an experiment and some simulations. So summarizing a little bit what I've said so far, what we have with SpinWaves is that the dependence of frequency versus K vector is highly dispersive. Okay, this is something we've seen, and it can become much more complicated. And also there's a gap. You see, there's a gap here, and this gap can be controlled by the applied field. We saw that in the previous talk, and Tim mentioned that it's quite interesting. You can shift the resonance frequency by applying a magnetic field. Okay. Of course, there's other effective fields that come from the geometry of your sample. So also changing the geometry of your sample, you can completely change this dispersion relation, and we'll see right now. Before, I just put here, so look at this panel, just some of the, to me, interesting features of SpinWaves. So maybe I exaggerated here, but the wavelengths we're talking about are quite smaller compared to electromagnetic waves. Okay, let's see. Gamma. So I show you that M is gamma S, right? So gamma is usually about, for electrons, is 27 gigahertz Tesla, just to put some numbers, okay? So that means that depending on the strength of the interactions, we'll have resonance frequencies that are in the tens of gigahertz to hundreds of gigahertz, okay? At this frequency, an electromagnetic wave, a Wi-Fi in our cell phone, is about 30 centimeters, right? Yes, but now for a spin wave, we went down to hundreds of nanometers. So this is a big difference, and this is one of the main features that make it interesting for on-chip communication, right? So electromagnetic waves cannot be used in a chip to get interference, for instance, but spin waves, they could instead. The nonlinear dispersion relation is also interesting because you can have oscillators, you can have many things that give you fantastic physics, and also there's a non-zero frequency at zero wave vector, and this lift that you can even control it by external parameters such as the applied field. Okay, so let me get into move this. What happens when we go to the thin films? Okay, so we want to see spin waves in Spintronics. So one of the most used geometries are thin films, either stripes or confined systems. So the first type of waves we can see are the merely, okay, the pure exchange spin waves, and these are the spin waves that propagate in thickness. The thickness are quite low, so it's a few nanometers, tens of nanometers. So they propagate and they reflect back and interfere. So they create some kind of magnetostatic some magnetostatic spin waves, and these are called also thickness modes. Okay, and these are purely exchange waves because this is a very short range. For very thin films, you don't see that. So you see these when you have tens of nanometers. Okay, so actually Kittel, we also saw already the Kittel formula. Actually, Kittel derived the dispersion relation for a dipole exchange, both spin waves, in an infinite ferromagnetic material. Okay, this is not a thin film with borders. This is an infinite, but you can see that if you look at k equals 0, we get the gamma h that we knew. And also there's something interesting, which is that the propagation in the direction of the applied field is different than the propagation perpendicular to the applied field. Okay, so we have a diagram here, and this for a thin film, and I show you the frequency versus wavelengths, wave vector. And you can see that depending on the direction of the applied field, you get quite different dispersion relations. One is called forward volume, the other one is backward volume. The reason is that one, you can see that the derivative of F versus K, which is the group velocity, is positive, and in the other one is negative, right? So that's why it's called forward and backward. But I don't want to get much into naming, I told you before. But it's important to know that the dispersion relation, that's it, the F of K low is a very anisotropic function, even in an isotropic magnetic medium. This is important. So we can tune it, we can engineer it, but even so, if you just get an iron thin film, a cobalt thin film, the propagation in one direction or another direction when you apply a magnetic field is different. Okay, I just mentioned that there are relations with magnetic resonances. In principle, but maybe Adriana will tell you something different. When K is equal 0, if there's a common resonance in the magnetic moment, this is what it's called ferromagnetic resonance. We have others like electron nuclear magnetic resonance, but in Spintronics, basically, we work with magnetic materials with a strong interaction, so with exchange. And then we have ferromagnetic resonance. What I'm saying is that FMR is basically a spin wave technique with K equals 0. Okay? But anyway, I'm sure Adriana will tell you more about this. Okay, let me keep going to just stay a bit on time. So next, what I'll do is to discuss a bit in the next 5-10 slides how to create spin waves and how to detect spin waves. These are what I consider the main means to do that. Of course, you can have other means and you can combine them, okay? But in this lecture, ideally, I want to show you that, okay, one way to create the spin waves is just create an oscillating field. So again, I wrote the Landau-Lifshitz equation, the equation of the dynamics of magnetization. And what we do in here is to create an effective field, a magnetic field that it's oscillating. So it has a component that oscillates. And that means that you will have something oscillating here, also here, but now I'm not interested in that, that's going to create some dynamics in your moment. Okay? So then we can create some particular excitation on a thin film, and that could propagate. This is not very efficient, but this works very well, and it can be used to study films or to create devices. Of course, we need thin films. This is nickel that have, let's say, good propagating distances, okay? Low dampings in this case. Here's an experiment that shows that you have an antenna, and if you put it in a stripe thin film, you can create different propagating waves. And actually, you create some magnetostatics in one dimension, and in the other dimension, you create this in Kx, you create this dispersion relation that it's the one we found also for the magnetic chain. Okay, maybe using a magnetic field was the way we all knew and everyone might guess, but there are other means to create spin waves. And one is the spin transfer talk. So we've seen that in the talks on Monday, and you'll see more about this on Friday. But the spin transfer torque is basically an exchange of momentum between itinerant electrons that pass and cross a magnetic layer or a magnetic material. So you have to have conservation of angular momentum, and what happens is that the material is kind of filtering the electrons. So there's an exchange of momentum, and on the one hand, you change the momentum of the spin of the electrons, the itinerant electrons, and also if the magnetic material is thin enough, you can also change or modify the magnetization of your layer. So the way to model this is we have precession in blue, we have damping in green, and then we have this additional term, which is the spin transfer torque. So the spin transfer torque, if you looked at it, it's like, it's an effective damping. You see, though, it's M cross M cross. MF is the polarization of the current that you use to create this excitation. So eventually, if we do it properly, this beta basically depends on the spin polarization, the current intensity, and many other things. But if you make this to have the opposite sign of alpha, what you do is that alpha is the damping, in green, right? And the spin transfer torque could act opposing the damping. So if you have the right geometry, just with the DC excitation, and this is important, before you had to use an AC frequency with the effective field. Now with the DC excitation, you can create an effective negative damping, and that leads to magnetic excitation. So if you do that in a confined area, you have nanopillars, so this is used in memories. But if you do it in an extended thin film, you can create, these are the spin torque nano oscillators, and you can create propagating spin waves. You can also create spin waves with light. And this has some advantages. So you can see in this cartoon that you use light to pump, the first one. So you create an excitation, and then you can even read it with the same setup, let's say. Actually, I mean, you can connect, in this article, they saw that the dispersion relation was different, or was actually following the theory when it propagates in the direction of the applied field or in the direction perpendicular to the applied field. What's interesting from light-induced spin waves is that this only works in certain materials. So in fact, they have to be ferrimagnets. Ferrimagnets means that you have two lattices, one with the spins in one direction and another one with opposite direction, with a smaller magnetization. And the way it acts, it's completely different. It's a little bit unknown yet. But what happens is that it usually has a much faster time scale. So it could be of the order of terahertz, which is the exchange between the two lattices. And this is under investigation, but it's quite promising because light is something not too expensive, and it could create, you know, a new field of study, which is the terahertz spin waves. So finally, I show you also how to create magnetic waves with the strain waves, because this is something I did recently. The nice thing of strain waves is that phonons 1 gigahertz phonon in a piezoelectric material happens to have a wavelength that is also of the order of microns. So then we can do a match between the wavelengths of, so this is a piezoelectric and this is a magnetic material. So in principle, because of the magnetoelastic effect and magnetostriction, if you press, compress, and decompress a magnetic material, you can create magnetic excitations. Okay, let's go to the detection. So in somehow we have the counterparts of what I showed you in the creation. So we can detect magnetic excitations just reading the dipolar fields. So also with an antenna, right? We can use magnetoresistance. So the giant magnetoresistance is telling us that if you put the reference layer, let's say this is the reference layer, if you have an excitation here, it means that you're changing the effective lengths of this magnetization vector. So if you read the R versus T, you will get an oscillation. So this is one of the ways to detect spin waves, but you have to make a point contact and pass a little bit of current to measure the resistance. One of the nice experiments is that if you pass current in one contact, so this is the magnetic layer. So if you pass current here, you excite spin waves, and actually you excite spin waves in another one, and actually you can read in the same nano contact, and you can see that both synchronize through the spin waves. So there's some constructive interference, and that was shown about 20 years ago. Okay, I'm going fast, but I want to finish this. So I apologize. But brilliant light scattering, this is a technique very, very useful, and that you have to hear about it if you talk about spin waves, because this is probably, I mean, without using microscopy, you can get information about both frequency and wavelengths. Why? Because well, this is the light scattering. This type of light scattering is combining the incident photon with K and F, and it's getting information about frequency and K vector of the magnon in your system. So by doing this, you can directly map a system and do this nice graph that you can see here, which is frequency versus wave number. And you don't have to excite anything. You just shine with light, you change the incident angle, and the incident angle is setting the spin wave vector that you can be sensitive to. Okay, and what you are detecting are just thermal spin waves. So this is just a way to characterize any thin film or any magnonic device. Okay, but advances on this technique have managed to be able to do some microscopy. It's called micro-focused brilliant scattering. And then what they do is like they focus on a particular spot and they see what are the excitations there. In this case, you have to excite by another means. So in these three examples, they excite in an antenna here. So spin waves propagate in this direction. In here, the same, they excite it from here, and they see that under certain conditions, spin waves can turn in a straight line, in a curved line. And in here, what they show is that exciting spin waves in this direction with the electrical current, you can decide whether spin waves go in this direction or in this other direction. So these thoughts, this is about how to modify spin waves, and this is an excellent technique to do these experiments. Okay, one more, optical microscopy, Kerr effect. So the Kerr effect is just a rotation of light in a reflection when it interacts with the magnetic material. So it's similar to Faraday, and you can get information. You can do microscopy if you have a camera, and you can do also time resolved. So that's a very interesting technique, and many studies use this type of experimental setups. Okay, just a brief mention of X-rays. So we can use X-rays to investigate spin waves. Why? Well, I mean, there are several good things of X-rays, and probably next talk will give you some introduction. And actually, I'm not sure if it's next Friday that Lucia is giving a talk, and it's based on X-rays. So the X-rays, the L3 edges of a material basically go from 2 to 3D orbitals, and these are the responsibles of magnetism. So if you shine your material with polarized light, one direction, or in blue, the other direction, what you get is that you get a differential absorption, and this differential absorption is proportional to the magnetism. Nice thing of this is that this is element specific, so you can focus on iron. So no matter if your material has also manganese or nickel, you're just focusing on what iron is doing. What's interesting of this? Well, I mean, you can do, here I'm just showing two types of imaging, but of course you can do good spatial resolution, so you can get information on the wavelengths, and you can also do time resolution. I mean, normally in synchrotrons you have bunches of light that, I don't know, whatever, nanoseconds, so you can synchronize to that and do some stroboscopic measurements. So in general you can get both time resolve and space resolve. So to keep on time, I'm just gonna, okay, I also put here the spin pumping because you've heard about it as well. And you know that when you have a magnetic oscillation, you're pumping spins through whatever you have there. So if it's a substrate, you do it through the substrate, whatever. The thing is that if this other material where you're pumping spins, it can convert the spin current into a charge current through the inverse spin Hall effect, then this is a means of detecting spin waves or detecting magnetization dynamics. So this is kind of the opposite of the spin transfer tool, right? So with the DC current, we created AC magnetic excitation. So now with the AC magnetic excitations, we get a DC electrical current. Okay, so finally, in the last, let's say 5 minutes, I just very briefly, I'll show you some of the uses of spin waves. So I'll say the main goal is to carry and process information at the nanoscale. This is my consideration, but things that people try to do. So on-chip communication, this is important. I mean, we have developed a lot of communication protocols for Wi-Fi, and all work at the gigahertz frequencies. So we can translate exactly the same on chip, right? And also there are many different proposals for computing with waves and create kind of a new paradigm. Why? Well, because there are new proposals similar to quantum computing or neuromorphic computing, and also because spin waves happen in materials that are already implemented or integrated to the electronics. So we are not talking about something completely different. So we can use the materials that are used in electronics and spintronics. Okay, just to recall fundamental properties. So we have frequencies that range from gigahertz to almost a terahertz. The wavelengths are in the nanometer scale to micrometer scale. And also, if I don't mention these, the energies are of microelectron volts. So this is wrong. Microelectron volts, which is, you know, I mean, it's 1 Kelvin. So at room temperature, there's no problem to get all this. We've seen that spin waves can be excited of several means, can be detected as well. They can be transferred. And here it's very important to control the damping parameter because this is what sets how far you can go with spin waves. And actually it can be modified. How do we modify that? I show you that the dispersion relation could be complicated or could be very different in materials. But ideally, we like to do that in a functional way. So in the same device, we can change the propagation, let's say, frequencies or wavelengths. So this is the magnonics field, and the magnonics field, it's kind of like photonics that tries to pattern or to engineer the materials in a way that you change in this case, the magnetic properties, so that you see in photons, you have a linear dispersion relation. And with a photonic crystal, what you can create is you change this into something that creates a gap. This if you need a gap. So in magnonics, you can get the same. So we have a dispersion relation that's not linear at the beginning, but still we can change it or engineer it, just changing the properties of the material. And I'll make a summary here. Let me just put it on so we don't get. So if we looked at the frequency versus K in a thin film, I show you before the Kittel formula for a ferromagnet, an infinite ferromagnet. This is for a thin film, and a thin film with a thickness D, with some width, and also with some magnetization saturations, not the same nickel than cobalt, and with an applied field. So any of these parameters is affecting the frequency versus K. So you can either change the magnetic field with some patterning of a wiring. You can change the thickness of the material by some lithography. You can change the saturation magnetization by changing the material or by implanting some ions and reducing the magnetization. And you can change the width as well, just doing some patterning. So as examples, I put you these two. So in the first one, what happens is that in two strip lines, one without anything, nickel iron, so this is permalloy, and another one with the same material, but with some ion implanting to reduce the magnetization. And you can see that the orange one is the reference, and the other one you created some gaps. This is not fortunate color, but you create some gaps that forbid certain frequency propagation. Okay, how do we compute with waves? Just some ideas. Let me see. So for instance, this is just an example, and I'll finish here, I think. So if you have two strip lines where you can propagate the same spin wave, then you can create different inputs, and these inputs are meant to create a small delay. If you create a small delay in the output, you can get constructive or destructive interference. That means that you can create logic gates. This could be at the nanoscale, and in principle, the energy you need, if you manage to find a good way to create spin waves, this is quite dissipationless. I'll finish here because I think it's better to stay in time and take questions if you have some. So, well, I'll thank you all for staying, and I hope you enjoyed the talk and you can get at least something out of it. Okay, so thank you.
Thank you for being in time. Very nice talk. I'm clapping my hands, and we do have some questions already after this very nice talk. So the first one is from Pradeep. Thanks for the nice talk. In case of a spin transfer torque induced net negative effective damping, we excite auto oscillation. What kind of a spin wave mode this oscillation would correspond to, and how these modes will be different from the other fundamental modes present in the systems, such as the ferromagnetic resonance mode?
Okay, sorry, could you repeat the first part, because I just changed the
okay.
screen?
Yes, in case of a spin transfer torque induced negative net effective damping, we excite auto oscillation.
Right.
And then what kind of a spin wave mode this oscillation could correspond to, and how these modes will be different from the other fundamental modes present in the system, such as the ferromagnetic resonance mode.
Okay, the ferromagnetic resonance mode, usually you use coplanar waveguides that the dimensions are almost millimeter scale. So that means that the non-uniformity of the effective fields you create are very, very low. So you can consider that everything is processing at the same phase. Okay, in a spin transfer torque contact, usually the contacts are 50 nanometers, 100 nanometers. And this is almost the wavelengths of the wave vector. Actually, if you solve the equation of Landau-Lifshitz, what you see is that the wave vector is set by the size of the nanocontact. Okay, but as you go far away from your nanocontact, if you get a material with a very low damping, what happens is that this is changing and is going to the fundamental frequencies. So if you excite certain frequency in this material, it corresponds to certain wavelengths. Okay, but I guess the answer to the question is that what sets the wavelengths is the size of the nanocontact.
Okay. So then our coordinator, the coordinator of this course, Fernando Bartolome, he thanks you for such a nice talk, and he has a question. Historically, but also nowadays, spin waves spectra have been measured by inelastic neutron scattering. Did you simply not mention neutrons as a way to detect spin waves because you are assuming nano-size samples only?
Yes. So somehow, I mean, I had to cut it, and my feeling was that, okay, in Spintronics, people are quite focused on devices, and it's like people also measure it just using squids and see the temperature dependence of the magnetization, but I mean, probably I should have included that. But,
okay. Another question from Lucas Fisher. Thank you for the nice informative talk. Can you elaborate on how one can tune the directionality of a spin wave emission? In particular, how can device geometries, material anisotropies can contribute?
Okay, there's different ways to do that. So as I told you, just by the intrinsic parameters of the material and interactions, you can get different propagation, let's say, properties. But of course, this is not that interesting, but that means that you have to come up with a different material or with a different device. But people have shown that current can be used to drive spin waves. So this is one thing. Strain can also be used to change the propagation direction. So basically, the idea is to change the effective magnetization, the effective field in a dynamical way. How could you do that? Changing the applied field. If you change the applied field locally, basically what happens is that the spin waves try to go in this direction. So people have shown that you put a spin transfer torque oscillator, and then depending on the distribution of magnetic fields, or if you change the distribution of magnetic fields, you can have the spin waves going in one direction or another one. You can get more complicated things like having two sources that interact. When they interact, you have constructive interference or destructive, and then if you have constructive, they go in one direction. If they have destructive, it's not destructive, it's destructive in this direction, so it goes to the other direction.
Mm-hmm. Okay, I have a question myself. I didn't understand well when you show a waveguide that divided in two branches, and you could control the propagation by applying a current. Can you put that slide, please?
Yes.
Because I didn't see the difference in one case or the other. I mean, how?
One second. What was it? Sorry, I'm trying to find it. Okay, now I'm sharing it, and let's see. Not this, huh?
No, before that.
Was it before?
Before, yes.
Oh, with the VLS.
Yeah, that one, yeah. That one. Because I didn't see the difference. I mean, the values of the current were the same, 100 milliamps. So I don't know if you are just applying the current in just one branch.
Yes. Yes. If you see in okay. Here, the current goes in this branch, and here the current goes to the other branch.
Okay.
So you're kind of helping. So it could be that just, I mean, there are many ways to do that. You can just heat locally some part and you'll lower MS. I mean, there are many ways to do that. But in here, they show that you can direct it with an applied current. So
then you need a switch, let's say. It's not by changing the value of the current, but by changing the electrode. I mean, or...
Exactly. I mean, there are many, as I said, there are many proposals on how to use spin waves, but it's not clear to me what is the, how to say, the direction to take for precise devices. So there's no devices that it's like, okay, this is a market device and we have to go for it. Because as you said, you identify that there's a switch here, but probably you can identify that there are also 100 milliamps current, that it's not that suitable for an application.
Okay, then we have a last question. Well, it's not a question, it's just a comment from Mergin saying, that's very nice, illuminating talk. Thank you very much. So
thank you.